In this video, we're going to look at some examples with sequences. The first problem being a problem directly from your homework, and then just some quick examples with arithmetic and geometric sequences. So for the first problem that we have here, we're given the first few terms of the sequence, and we're being asked to find the nth term. Finding the nth term is actually really handy. We don't have too many questions on this subject, but I just want us to sort of talk a little bit about it. So the first thing you want to look at is you want to look at a pattern. In fact, that's going to come up again when we look at examples a little further down the page. So what you notice is the first term is the first term is 2. The next term is 4, which is 2 times 2. The next term is 8, which is 2 times 4. So what we're seeing here is that every term is double the term that came before it. And that is the definition of a geometric sequence. So we're not told that this is a geometric sequence, like we're not given that information, but we can see ourselves that it's a geometric sequence where the first term is 2, and then r, which is also known as the common ratio, is also 2. So if you remember in our previous lesson, we talked about the fact that in a geometric sequence, the nth term can be defined as the first term times the common ratio to the power n minus 1. Well, in this case, since the first term and r are the same, that'll translate to 2 times 2 to the power n minus 1. Oh, and that's just 2 to the n. Okay? So in some sense, we almost didn't need the fact that this is a geometric sequence. That was just kind of a handy observation. But sure enough, the nth term of this sequence is 2 to the n. The next two examples are kind of further taking us down the road of arithmetic and geometric sequences, so we get some practice with those. So arithmetic sequences are ones where there's a common difference. So K is the common difference between any two terms. Common difference. And here we're given that the first term is -6. So let's write out the first few terms. So a sub 2 is going to be a sub 1 plus the common difference, which is -3. A sub 3 is going to be -6 plus the common difference, which I want you to notice is the same as -6 plus the common difference plus the common difference again, right? So that'll take us to 0. And the reason that I wanted to make sure to write the third term in both of these ways is so that you saw. So like, for example, when we go to write the fourth term, we can write this as 0 plus 3, right? That's the third term plus the common difference. But that's the same thing as -3 plus 3, which is the same thing. I should say -3 plus 3 plus 3, which is the same thing as -6 plus 3, which is -3, plus another 3, which gets us 0, plus another 3, which gets us to 3. So what we're noticing is that every term, a sub n, is -6 plus 3 times n minus 1. So for the second term, we're adding 1 3 to the first term. For the third term, we're adding 2 3s to the first term. And for the fourth term, we're adding 3 3s to the first term. So this tells us that a sub n is -6 plus 3 times n minus 1. And once we're given this information, now I can find the, 5 millionth term, right? I don't need to know the term before it. I simply take n, which is 5 million or something else, subtract 1, multiply it by 3, and add to negative 6. Moving on to the second part of example 2, the question is this an arithmetic sequence? So remember, an arithmetic sequence is a sequence that has this notion of a common difference. So the difference between any two consecutive terms is the same. So let's look. What's the difference between 3 and 3/2? So it might be helpful to think of 3/2 as 1.5. So between these two terms, the difference is 3/2. In other words, we would subtract 3/2 from 3 to get 3/2. How about this one? To get from 3/2 to 0. Well, that looks good so far. We would subtract 3/2 from 3/2 to get 0. And then the last pair that we have here is 0 to negative 3/2. And sure enough, once again, if we subtract 3/2 from 0, we get negative 3/2. So the answer here is yes, this is an arithmetic sequence. Okay, so now let's move on to our example with geometric sequences. So remember, a geometric sequence is one where there is this idea that every term is the term before it multiplied by some number. So in the previous lesson, we called that number r. Here I will expand on that to say r is the common ratio. So let's introduce that term here, common ratio. So the reason it makes sense to call it the common ratio is that this is the ratio between any two subsequent terms, or any two consecutive terms. So let's check it out. So a sub 1 is 3, a sub 2 is 3 times 5, which is 15. A sub 3, so here you're going to notice an immediate similarity with the arithmetic sequence example, right? So we take the previous term and we multiply it by 5. But notice that that's the same as taking 3 times 5, which is our second term, and then multiplying it by 5 again. So just like the same idea that we saw with arithmetic sequences, we have our first term. For the second term, we multiply by the common ratio once. For the third term, we multiply by the common ratio twice. So very, very similarly, we see, and let me write it in red to be consistent, that the nth term is the first term times the common ratio to the power n minus 1. So again, for each term, we're multiplying by one fewer times the common ratio than the number of the term. So if I asked you, hey, what's the 12th term here? Okay, well, you would say that it's 3 times 11/5, or 5 to the 11th power. Of course, 5 to the 11th power is a very large number, so I'm not going to write it out in full, but that would be the 12th term. So what you're seeing here is something that we actually discussed in our previous lesson, which is that when the common ratio is greater than 1, the terms of the geometric sequence grow very, very, very quickly. For our last example in this lesson, here is a sequence, and I'm asked, is this a geometric sequence? Notice I'm not being asked, hey, find me the nth term regardless of whether or not it's a geometric sequence. This is a yes or no question. So exactly the same way that I looked at the arithmetic sequence, I'm going to look to see if there is a common ratio. So to get from 2 to 6, you would multiply by 3. This looks good so far. To get from 6 to 18. Oh, well, this looks good. To get from 6 to 18, you would once again multiply by 3. Oh, but we have a problem. To get from 18 to 36, you would not multiply by 3, you would multiply by 2. So right away, we see this is not a geometric sequence because there isn't a common ratio, there isn't a common number by which we would multiply all the way through for each consecutive term to get the next term. So just a little bit of examples on sequences to get us a little bit more comfortable. In the next example, or I should say in the next lesson, we'll look at taking the terms of sequences and adding them together. So we'll introduce summation notation, we'll introduce the idea of partial sums, and we'll even mention a little bit about something called series. That's the end of this lesson.